Okay, guys, welcome back. This is day 7 of gravitation, I guess. Yesterday in yesterday's class, I remember discussing gravitational fields for different bodies and the fields in between the relation between gravitational fields and potentials. Also, talked about fields and potentials, how we relate them in different cases. We in fact came up with this ND equation saying. Minus dou v by dou r equals to E. Like we use this idea to find the fields, the relation between the fields and potentials in a lot of problems. Even gave you a problem saying v equals to, yesterday it was 2x plus 3y, right? And when we differentiate it partially, minus dou v by dou r is actually minus dou v by dou x plus dou v by dou y plus of obviously dou v by dou z I cap, j cap, k cap. Since there were no z terms, there aren't any z terms. I'm neglecting this part. We only differentiate it with x with respect to x and with respect to y, and then we get the value. So it was a bit confusing yesterday, so I will just give you one more question on that just to get a better perspective. Let us say the potential is given as 2x square y. Yesterday it was 2x plus 3y. So please clearly observe. Yesterday it was 2x plus 3y. Now I'm giving it as x is 2x square y. I want the field, gravitational field. How do I do it? If I want the gravitational field, all I have to do is minus dou v by dou r. So I have to differentiate the whole thing with x I cap and then differentiate Sharat. Sharat, what is it?
So I wanted to say the same thing, sir. That's it.
What?
Partial differentiation.
Partial differentiation, yeah. But how do I do it? How do you do it? Stay in line, but tell me, how do you partially differentiate?
Sir, first, sir, while partially differentiating with x, we'll have to consider 2 and y as constants.
Exactly.
So we'll be getting 2y into 2x, sir. Then for dou v by dou y, we'll have to consider 2x square as constants. We'll be getting 2x square.
Exactly. So guys, watch this out. Like all I did is simply in the place of v, I put 2x square y in both the cases. I simply put 2x square y in both the cases. I got this. Now I have to differentiate. So when I differentiate, I can take out the term 2y and only differentiate x. In the second case, I can take out 2x square out. I can take 2x square out, only differentiate y. You getting my point? That is the partial differentiation idea, the idea of partial differentiation. We did the same thing yesterday only. We differentiated the entire thing. We only got like this part for x and we only got this part for y because the others were constants. So when I differentiate it, I get minus 2y into 2x I cap. 2x square into this differentiation gives us 1 j cap. So this is a field equation. It looks so complicated and the field is complicated because the potential equation was complicated in the first place. Okay. I'm going to give you one more problem just to gain a lot of confidence for you people. Try this problem also. Aditya, what did you give the answer as 4x minus 1? Why? No, the answer is this. Minus 4xy I cap minus 2x square j cap. This is a field equation. Aditya, didn't you understand this part?
Yes, I consider that into thing like how we did for plus.
No. So like this is the final. Let me give you another question. You people try to answer this.
Okay, sir.
Potential is given as x cube y plus y square. I want the field equation. Take a minute and try to give me an answer. Try to raise your hand if you get an answer, please. All you need to do is again the same part, differentiation by r, which means partial differentiation I cap partial differentiation of y by j cap plus the partial differentiation with
Sir, I got a complex answer again.
Sir, x cube plus 3x square y plus 2y, sir.
x cube. Where is I cap, j cap, and k cap? Where did they go?
Sir, can I say?
Yeah, Aditya, give me the answer.
Sir, 3x square y I cap
3x
plus
square y I cap. Good. Next.
inside bracket x cube plus 2y j cap.
Beautiful. Is there any z?
No, sir.
No, sir, no z. Why
That's good.
z would
So
come?
guys, watch this. I'll repeat what he just gave. I mean the answer he just gave. Dou by dou x of x cube y plus y square I cap. Again, dou by dou y of x cube y plus y square j cap. I'm not writing k cap because there are no z terms at all. I'm not caring about the z terms at all, so I'm not giving any z terms. Now let's go ahead and differentiate this thing. Let's do it. So we're talking about minus. We're talking about minus dou v by dou r, which is nothing but the electric field. Sorry, the gravitational field. So the gravitational field comes as minus stuff. Differentiate this whole thing only with x. It's as if this part becomes 0. Only x cube y. So I get 3x square y. Because y is a constant, I keep it aside. So this whole thing gives us I cap. Now I differentiate the whole thing with y. Here x cube is a constant, so x cube stays exactly like that. Dy by y is 1. Now differentiation of y square is 2y j cap. So this is the answer, guys. You will definitely get a complicated answer. Yeah, Harshita also gave the same answer, it seems. Minus 3x square. No, yeah, minus 3x square y. Harshita, you gave some other answer. I don't know why. But be careful with this part. Maybe you're doing it wrong in the partial differentiation of y. But even though you learn it, it's not really that important, guys. You don't really need it, okay? Because this is like an advanced idea. Vamshi, what is it?
Sir, how x cube came, sir? X cube plus 2y there, sir.
So yeah, what's this thing? Partial differentiation of this whole thing, right?
Yes, sir.
I can take x cube as a constant and dou y by y, dou y plus dou y by y square.
Okay, sir.
You get it? So x
Yes, sir.
cube into 1, this part is become as 2y.
Oh, okay, okay, sir. Understood, sir.
Right? Guys, you don't really have to worry about it, okay? Like this is very a very high standard value. Since you people, I really thought you people already know how to do partial differentiation. That is why I kind of jumped into this idea, but then I realized it's not over for you. So I'm taking it slow. Like I clearly gave you some problems on that. Now, what if somebody gives you field equation like 2y plus 3j cap and asks you the potential? What if that's the case? Anybody who's unmuted? No. This is what we talked about. I hope you remember the equation.
I was about to say this equation only, sir.
Yeah, so
Same thing, sir.
like I hope you remember both the equations. E equals to minus dou v by dou r, and this part v equals to uh, EDR. Now, what you need to do is like the integration is a bit tricky. All you need to do is divide this into x parts and y parts separately. I'll show you how to do it. 2y cap plus 3j cap. Somebody was asking how to do differentiation with integration with vectors involved. You see what I did there? I
Yes,
wrote
sir.
the field normally. I wrote the vector as dxy plus dyj. So when we do this, the minus remains like this. I dot I only, you will get 2dx plus integral 3dy. That's all. Integral 2dx plus integral 3dy. If you integrate it, you will simply get minus 2x plus 3y. So this is a potential equation. Why don't you, like for practice, why don't you take some potential equations, try to convert them into field, and try to take some field equations, convert them into potential equations just for practice, okay? Again, this is some high standard ideas for you people. You don't really need it. Okay. In H.C. Verma, he gave the same problem. Like he gave the E value. He doesn't even ask the potential value. He says, a body travel from this point to this point, like 1 comma 5 1 comma 5 to 5 comma 2, let us say. It traveled from this point to this point. What is the work done? Aditya, how do you do it?
Sir, we have to do this integration vectorially, sir.
First of all, work done is nothing but mass into potential
Into-
difference. So
Yes, sir.
work done equals to mass into potential at 5 comma 2 minus
Yes, ma'am, I
1
submitted.
comma V final minus V initial, right?
Yes, sir.
Now, how do you find potential in 5 comma 2, 1 comma 5?
So first we need to know from which it is going, sir.
First of all, we
Like,
have this equation. Remember?
okay, this equation is in this
Yeah,
also.
you already have the equation for potential. So just put those x, y values in this thing.
Oh, I thought that is a different question. This is a different
Oh,
question.
no. I'm talking about the same question. Okay.
Okay.
So why don't you guys do it? Like I'll just give you a different value. E equals
Yes, sir.
to
I'll try.
5x, 5i cap plus 5i cap plus 3j cap. This is the gravitational field value. And now find the work done in moving a particle from 1 comma 3 to 5 comma 4. Like I said, the path doesn't really matter. Let us say we actually travel like that. I want the work done. I'm giving you 1 minute. Try to give the answer as quick as possible. Harshvardhan already gave an answer. Let's see who else gets the answer quick. Harshita gave the same answer as Harshvardhan. Okay, good. Any more answers? Anybody? Sharat gave a different answer. Sharan completely gave a different answer. Anyone else, guys? Chetan.
Sir,
Chetan.
23M.
23, sir. Same 23M.
23M. Okay, but yeah, Harshvardhan and Harshita also agree with the same answer. Mahasida also says the same answer. It's just Sharat is getting all different answers. I don't know why. Okay, let me just do it for the rest of the people. Okay, since we're doing it, V equals to minus EDR. V equals to minus E is nothing but 5i cap plus 3j cap dx I cap plus dy j cap. So to put it really clear, it is 5dx plus 3dy. 5dx plus 3dy. You can in fact find the answer from here, this point itself. V equals to minus of integral 5dx plus integral 3dy.
So we have to
You
put the
can
limits, right,
put the
sir?
limits of x and y right here itself. Like where did it start from? It started from 1 comma 3 went to 5 comma 4, right? So
Yes,
you
sir.
can put the limits of x as 1 to 5 here, 3 to 4 here. You'll get the answer, the potential difference, delta V. You'll get the delta V. When you multiply it with mass, you'll get
Sir, this
delta U.
lonely screen is coming, sir.
Uh, so guys, check it if you are getting the right answer or not when you're doing a problem like this. You're not, aren't you supposed to get a negative answer? Everyone gave a positive answer except for Sharath. You're supposed to get a negative value.
Yes, sir, negative 23 by m, sir.
Yeah,
Yes,
because
sir,
there is a
negative.
negative sign, then there's a negative sign is coming. Can somebody
I
tell me
I get
why
it.
was there some negative work done?
Because we have to give like,
Why was
yeah,
there a negative work? Sharath,
because we have to give it, sir. We have to do some work instead of getting.
Sharath,
So we're going in the opposite direction, sir.
I'll show you. Yeah, Sharath, you are right. The field was given as how much? 5i plus 3j, right? Is it?
Yes, sir.
5i plus 3j. Which means the gravitational field is already acting like this, somewhere like this, right? 5i plus 3j, both are in the positive direction. So this is where the field is acting. So when you put a mass in here, the mass is already intending to go in that direction. The mass is already intending to go in the direction. Now, to start the mass from 1 comma 3 to end it 2 comma, where did I end it? 5 comma 4,
Five
to
comma
end it at
four.
5 comma 4, which means I have to stop it at 5 comma 4. The mass has to start and it has to stop at 5 comma 4. If only I simply leave it, it will go in that direction anyway. It will go in that direction anyway. I have to do some external work which is in the opposite direction, slowly, like stopping the body. It is like someone is pulling that body that way. The gravitation is pulling it that way. I'm trying to stop it at every point, and by the time it reaches, I stopped it. It's like that. So that is why the work done is coming as negative. Again, this is all some practical thinking. Like if you really develop this kind of sense, this is really helpful for your understanding of potentials and fields, not just in gravitation, also in electrostatics. Again, it's not really that important when it comes to a mains exam approach. Okay, it just builds up a really good intuition towards when you towards the idea of the gravitation field and potential. That is why I talk about this a lot. Okay, now once you get this clarity about it, let me take a new note. Yeah, let's talk about planets and satellites. Let's talk about planets and satellites. Now, oh, there are a lot of people in the waiting room, but I don't know who is who. I'm sorry, guys. Planets and satellites. Let's talk about planets first. Satellites come later, maybe like 2 or 3 classes later. Let's talk about planets. The first big assumption that we make about every planet. What is the biggest assumption, Aditya, since you're unmuted?
Solid sphere. It is a solid sphere
Just imagine it is a solid sphere of
with uniform
uniform
density.
density.
Yes, sir.
This is the biggest assumption that we make. That is not
True,
clearly.
sir. Because we have layers, na sir,
We
different
have
layers.
different layers at different levels. So the
Mantle,
densities are not equal, and the bodies themselves are not spherical. They're a
yeah.
little bit out of shape. Okay, so
So it
all
is
these
flat
things.
at poles.
Yeah, what?
Earth is flat at poles, it seems.
We
Uh,
say it is flat at poles, but
Not totally, but
compared to the size of Earth, like taking the size of Earth into consideration, all the flatness. Do you really know, like, if I draw a perfect sphere, can I draw a perfect sphere in this? Let us see. In this app, I can't draw. Yes, there's another app where I can draw a perfect sphere. So anyway, if I draw a perfect sphere, do you know that even the biggest mountains like Everest don't even show up like a small bump on the surface? So compared to the size of the planet, they are not really considerate, but we just simply consider it. We don't really need all those things. We simply consider it as a solid sphere and approach at all the problems. Like, why do we do that? At least if we can do it for a solid sphere for now, we slowly develop some sense, and in the future we can do it for different kind of densities and different kinds of layers. We will do that. Sharath.
So I wanted to say the same thing, sir, that it's a solid sphere. Like we consider that it's a solid
No.
sphere.
So first thing is we consider it as a solid sphere. So solid sphere has field outside the solid sphere for sure. We all know that. And it also has field inside the solid sphere also,
yes, sir.
except the field lines are different. I mean, the field intensities are different. On the outside, it is gm by r square. On the inside, it is gm by r cube into d. Okay, so this is how you write the fields outside and inside of a solid sphere. And we all know that the center, the field is 0 and all the things. But how do we relate, how do we bring this into our normal day terms? Instead of considering it as a solid sphere all the time, we do some things so that we can relate it with our things, like our daily terms. What do we do? The first thing that we do is we stand on a planet at a distance r. We stand on a planet at a distance r. We all know the field acting is gm by r square. So because of that, gravitational force equals to gm by, okay, wait, gm by, come on, I supposed to write it. Gm by r square is the field into mass of that man. That is the force acting on a man who's standing on the surface. Instead of taking this, we simply started calling this as weight. We simply started calling this as weight, and this as small g, and this as mass of the man. So see, that is why weight of a man has become simply mg, where g is called as what? The acceleration due to gravity. In the beginning of this topic, somebody actually questioned that, which is quite good. That we always define field as what? The gravitational field as force acting per unit mass by force acting per unit mass, force by mass. But isn't it also acceleration? Yes, it is acceleration. But I've shown you a difference. To talk about acceleration, you're supposed to put a mass there. The mass should accelerate, then you talk about acceleration. But to talk about field, you don't need to put any mass. You can directly talk about field. So dimensionally speaking, yes, a gravitational field and acceleration due to gravity, they're same. But acceleration due to gravity, a r, which is also nothing but g, the a value is nothing. So basically, like I can clearly tell you, e, a, g, they're all the same things. E, a, g are the same things. But you can only say only these two are same, but this is different. This exists even though you don't put a body there. These two are basically the same thing. Since it is for planets, or since it is for Earth, we call it as a small g. Also, since it is because of gravitation, we call it as a small g. Otherwise, a and g are the same things. Acceleration, this is nothing but also acceleration. All right, so that is why you call it as a acceleration due to gravity. Okay, so I hope you get that. And we are going to jump into those ideas really deep now. Okay, we are going to take a planet of mass capital M. This is where all the mathematics, all the calculations start. A planet of mass small m, sorry, capital M, and radius capital R. We can talk about all the terms like field and potential outside, field and potential line outside, and also field and potential line inside. Say they give you problems like there is a planet, at what height from the surface. This is how they state. They don't give you the distance from the center. They don't often give you the distance from the center. They simply give you the height from the surface. They ask you what is the field at some point, or what is the potential at some point. So this, when you write these things, like you already know the field is basically written as gm by the distance is r square, but the distance here is gm by, let me drag this. Can somebody tell me what is the distance here? It is r plus h whole square. The total distance is nothing but radius plus height. So that is how you write the field in terms of radius of the planet and height from the surface. We are simply converting all our simple body terms into planet mass and planet radius and height from the surface. That is where we measure everything from. And if we have to talk about the field inside, This is also an interesting fact. Yeah, this is a distance, but they only talk about the depth. So if you want to talk about the field inside, gravitational field inside, how much? Inside a point, gravitational field, yeah. Gm by r cube into d is the distance from the center, which is nothing but r minus d. Let me repeat this thing. You might get confused somewhere. I mean, like if you are lost somewhere, like let me bring it back to you. So what I'm doing is I'm taking a planet of mass m, a radius r. Let us consider a point here and a point here. This point is at a height h. This point is at a depth d. Okay. At a height h, field is nothing but gm by r plus h whole square. At a depth d, the field is nothing but gm by r cube into this. This is the separation. Remember, that value is nothing but capital R minus d. So the field outside the planet or on the surface of the planet, everyone knows the field is basically gm by r square. So if they want to talk about the field, they don't talk about in the terms of not just the distance from the center. They always measure the values from the surface, as if some height from the surface or some depth from the surface or on the surface. This is how they write the fields. And when it comes to potentials, it's exactly the same thing. Mass of planet m, radius of the planet r, some height h or some depth d, some height h and some depth d. So when you write the potential, it is minus gm by r plus h. Inside the potential, inside point potential, what? I don't remember the value, do I? I think I do. Minus gm by 2r cube into 3r square minus, this is the distance, small r, which is nothing but r minus d whole square. I am going to do this thing a lot, like directly use the formulas. Okay. That is the reason why I asked you to by heart these values really good. That is the reason why I asked you to make a table like Mr. Raghav did. And of course, there are some problems in this thing. I'm not going to say they're all right. I think this part is wrong and this part is a bit wrong. Okay. But rest of the things are totally fine. This is the kind of table that you need. This is the kind of table that you really need, so that you remember all these values, all the graphs immediately. It's just like when I discuss these problems, you'll immediately get the idea that what I'm talking about. So first importance thing is, like, they don't measure the distances from the center anymore. They clearly give you the distances from the surface. That is the first importance thing. And the second important thing is, like, we already introduced you to that idea. Whenever a man is standing on the surface, the force acting on him, how much was that? I discussed already. Gm by r square into man's mass. I call this as weight of a body. This is m and this as g, and we call this as acceleration due to gravity. So when somebody is talking about acceleration due to gravity, they're basically asking you to find the gravitational field itself. Again, like I said, those two are a bit different. But when you're trying to find the magnitude, you can totally find the magnitude of gravitational field and put it as gravitational acceleration due to gravity. It's totally fine. All right. So in problems, they say, like, one of the biggest assumptions again, when you have a planet, we always used to consider this g constant, if you remember that. In the problems of Newton laws, we always used to consider the values of g constant throughout. No matter how high you are going, no matter how low you are, we always used to consider they're all just constant values. That is because compared to the size of this planet, we used to go around up this height. No, that is also very big. Like the dot that I just put, can you even see the dot?
No, sir.
No, yeah, right. So even the size of the dot's displacement is like a huge height. That could possibly like some if this is Earth, the dot that I just put could be around 5 to 6 kilometers high. Okay, so we never even 5 and 6 kilometers is not really making that big of a difference. When it's not making a difference, that is why we didn't consider those ideas back then. When you're trying to find the acceleration due to gravity, we always used to take this as a constant value. Everywhere the value is g 9.8. That's all. But here we need to be really careful. First of all, do you want to find the value of g? Anybody is interested?
The capital G or small g?
Small g. Gm by r square. So all you need to do is put the value of capital G. It is better if you remember the value of capital G. Okay, I don't remember it. Anybody has remember that?
Sir, 6.67 into
6.67 into 10 to the power of
forgot that exponent.
Aditya.
So 10 power 11, sir, I think.
11 or minus 11?
Minus 11, sir.
Minus 11 into Earth's mass 6 into 10 to the power of 24 by Earth's radius 6400 into 10 to the power of 3 whole square. Can somebody grab a calculator and give me the answer for this thing? Are you seriously going to do that? Or it comes something around 9.81,
Yeah, 9.
something like that. We don't really need it. Okay, it comes around this value. Now this is where did we calculate it? On the surface. In the Newton laws, we always stayed near to the surface. We didn't really care about it. Okay, we didn't really have to care about it because we always leveled at the surface itself. We didn't really move very high, or we didn't really move really low. So we didn't really care about the value of small g anywhere. From this point onwards, I'm only going to talk about the small g only. Okay, so we didn't really care. But what if we are talking about satellites? Satellites, they don't just go around Earth. Or what if we are talking about an airplane? Airplanes, yeah, they don't really go that high, but yet they're compared to the other parts, they are high. They are at a height. So what is the value of g here? All you need to do is simply find the value of E, and that is nothing but g. How much is the E there? Gm by the distance from the center, r plus h whole square. That is the value. So I have the g at a height. The acceleration due to gravity at a height is gm by r plus h whole square. We can live with this value. We don't really have to change this value. But some people tend to approximate it, taking what if the h is very, very small compared to the radius. Let us say the radius, we all know the radius of Earth is 6,400 kilometers, right? Earth is the radius of Earth is 6,400 kilometers. Let us say I only went up to a height of 200 kilometers. 200 kilometers is very, very high, but let us say I went up to 200 kilometers. Compared to this value, this is very small. So in these kind of situations, if I have to make an approximation, what should I do? So they approximated this thing, g at a height. What am I writing? G at a height equals to gm by r plus h whole square. What I do is I take r common out from the board. R square 1 plus h by r whole square. I hope everyone sees what I just did. I simply took r square common out. So gm by r square, this whole thing will be written as 1 plus h by r power minus 2. There's a reason why I'm doing this. Guys, did I talk to you about the approximation? Guys, anybody? Did I talk to you about the approximations?
Sir, are you talking about significant figures?
No, not significant figures. Some about approximating this value.
No, sir, I guess
No,
no.
sir.
No. Anyway, if I didn't talk to you, just a small subtopic, very small subtopic. Not here. Let me take it on a different board so that a small subtopic. whenever I have 1 plus x power minus n or plus n, it doesn't matter, any number, and x is very, very small, x is like very, 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 very small compared to 1, I can write this as 1 plus nx. It's like if I have 1 plus x power 6, and I said x is very, very small compared to 1, I can write this as 1 plus 6x. The value is 1 plus 6x. We can do that. 1 plus x power 200 by 3. I can write this as 1 plus 200 by 3x. You can do that. Okay. This is an approximation you are going to learn in the future, maybe not right now, but try to just remember this idea. Like even though that value is negative, 1 plus x power minus 3.5, I can happily write it as 1 plus minus 3.5x. Okay, they call it as a binomial approximation, but we don't really need the solution for me, like the proof for this thing. All you're going to do is we're going to simply apply it here. Since this value h by r is very, very small, I'm going to apply it. Watch it. I just leave the gm by r square like that. I'm going to write 1 plus minus 2 into h by r. 1 plus minus 2 into h by r. So this is at a height, g at a height. So if I go further, I can write g at a height equals to, this is nothing but g at surface, remember, right? Gm by r
Yes,
square.
sir.
That is what the value at g at surface. This is a g at surface, if I remember that. So g at a height equals to g at the surface into 1 minus 2h by r. This is a thing that you might have seen this thing in your school days, maybe. In your school days, there are some people who might have seen this thing in your school days. When you go up, the gravitation value goes down. The value of acceleration due to gravity decreases. Now, guys, remember you can only and only and only, I will like put 20 onlys, use
If h is very less than r.
when h is very, very less compared to r. Now, how are you going to decide whether h is very, very less? Use it up to 200 kilometers, maybe 500 kilo. Using it 500 kilometers is a stupid idea, but it's fine, acceptable. But the bigger value that you're using it, the more wrong you're going. But it is always safe to use this or this, the very original idea. If you take this, I approximated. This is original. This works everywhere because this is nothing but gravitational field itself. We didn't do any approximation. This is original. Remember this. If the height is very small, you can use this. Okay, like when you go through your textbook, you'll find both the formulas. This is the original value. I'll round it up in red. This is the original value. It never goes wrong. It's always right. This is an approximated value. You can use this approximated when the height is very, very less. Again, what? Yeah.
Sir, like what if they gave like 500 only, and there are two options, one with this answer, one with that answer, then what should I do?
Always go with this one. Always go with the original one. If the original answer is available, always you should go with the original answer only. Okay, approximations are only available, I mean like acceptable when the original answer is not possible. Okay.
Okay, sir.
So like we'll have to do both sometimes.
No, you don't really have to do that. You'll clearly see that like most of the times they give the height as 10 kilometers max. They don't really give 100, 500, 1000. They don't do that.
Planes only fly
So if it's 10 kilometers, then we can directly approximate to g is equal to 9.8.
You can approximate it. You'll feel it, like the more you practice it, you'll understand the stupidity of this thing, so that you can easily deal with the stupidity of the problem. Okay. Let us go to a depth and find the field. We didn't go to depth, right?
Yes, sir.
Mass of the planet, radius of the planet. I went to some depth at D. So this is the distance from center, which is nothing but r minus d. So the formula of, at this point, I want g value. Let us call it as g at depth. All I need is gravitational field at the depth. How much is gravitational field? Gm by r cube into r minus d. This is the formula, gm by r cube into z. If this distance is called as z, that is a value. You should remember this formula since it is for solid sphere. You cannot ask me where these formulas came from ever. Okay, that is why I stressed it so much yesterday. Now I do one thing. So g at depth equals to, I'm going to write this as gm by r square into, I send one more r into this thing.
Yes, sir.
Just for fun. So g depth equals to, this looks like g at surface into 1 minus d by r. Now this is not an approximated value. This is an original only. And you don't need an approximation here. In the previous problem, you need an approximation because the calculations get complicated sometimes. But here you can always use this for the value of g at any point. Okay, guys, this is how you solve these kind of problems. Solid sphere, not solid sphere. Don't talk about solid sphere anymore. We're talking about planets now. So if you're talking about Earth, this is the acceleration due to gravity. At surface, we know. At some height, we know. At some depth, also we know. Now, what kind of problems do they give depending on this thing? What kind of problems do they give? I'll just give you an example. A man weighs around W at surface, some weight. At what depth he weighs only W by 2? At what height he weighs only W by 2? This is the question. At what depth he weighs W by 2? At what height he also weighs W by 2? His mass is not changing. What should change?
The height or
The height.
No, the acceleration due to gravity should change. So here it must be directly mg. Here the value must be mg by 2. Here also the value must be mg by 2, which means he's asking g at a height, which is how much the value. How do you write? Gm by r plus h whole square. It must be equals to g at surface by 2. This is about the first question when you're talking about the height. The second question, g at depth, which is the formula goes like, what is the formula? I can use any of the formulas. So I'm using any of those things. Gm by r cube into r minus depth. This must be g surface by 2.
yes, sir.
And I put g surface value as gm by r square and gm by r square. Once I solve these equations, I will find the height, I will find the depth, and that is what he asked.
So depth is half of the radius and height is root 2 minus 1 of radius, sir.
That's good. Those are the answers here. Okay, guys. I'll give you one more question. You'll clearly get it. Like, let us do the height question separately and depth question separately so that there is no confusion at all. At surface, he's weighing mg. And now I want some, at what height, I want height. At what height he's going to weigh mg by 4? This is the question, let us just say. Okay, so g at a height must be equals to g by 4. G at surface by 4. Let's write it as g at some height must be equal to g surface by 4. G at a height formula, gm by r plus h. I'm using the original only. Since the heights look
Sir,
so big.
same as the radius of Earth, sir.
Okay. GM cancels and it looks like r plus h equals to 2r. So h equals to r. Yeah, you're right.
So we can actually make a simpler equation out of this, sir.
Like what?
So we can take the ratios of it, sir.
How you get
Ratios of the acceleration is equal to
it?
square of
That's your
the
job.
ratios of
That's
the
your job.
distance.
You do it. Okay. So that is how you find the. Sometimes they give you a question like, what is the value of g at height at a distance 3r, at a height 3r from the surface. All you need to do is g height equals to gm by r plus h whole square. So gm by r plus the height of this thing is 3r whole square. You simply put the value. If they
Sir,
want you to
16, sir.
compare with the g
G
at
by
surface,
16, sir.
yeah,
G by 16, sir.
yeah. If you wanted to compare it with surface, you can compare g at surface is always gm by r square. So you compare this thing with the original value. It's just a normal daily problem again. Okay. Sometimes they give you problem with depth. Guys, please remember, only use this approximation, which is not a lot. We are not going to use this approximation a lot. Okay. We will be using the original field equation or original gravitational acceleration due to gravity a lot compared to the silly one, like compared to the approximation. The original will be used a lot, so please remember that one. And don't worry if you don't really completely get a hold of the topic. Once you practice enough problems, don't practice it this week because you don't have it for this week's syllabus. But if you're good with this week's syllabus, you can definitely go ahead and start practicing about acceleration due to gravity, which is small g. Now small g is definitely varying with height and with depth. We've already covered these two ideas. What else can it vary with? What else can it vary with? It is varying with height, it is varying with depth.
Mass density.
Mass? What?
Mass density, sir.
No. The planet is fixed. We fixed the planet. The radius is fixed. Nothing is changing. It's just positions, like at a height, at a depth, and what else can affect the value of gravitational acceleration due to gravity. This is a thing that I will teach tomorrow, but I'll just give you a glimpse of it.
Sir, rotation.
Exactly.
Rotational motion of the planet.
Because of Earth's rotation, for bodies who are here, they are going to feel some mr omega square. What is that? Pseudo force, centrifugal force. People who are here won't experience that much because the radius is smaller, r1 omega square. For these people, it's much lesser. At these people, they won't even feel this pseudo force. So because of this, gravitation here and gravitation here is also not the same. So gravitation at equator, gravitation at poles is completely different. It is a known fact, it actually works. The acceleration due to gravity at poles and at the surface is not the same. So you cannot use the same spring balance or the same weighing balance at the poles and at the equator. They actually, when they sell these what do you say, these weighing machines, digital weighing machines, especially when it comes to the weighing machines of like elements which are really sensitive, like if you're talking about a material which is highly valuable, for your example take gold. Okay, but there are definitely more valuable materials out there. So for those materials, if you just measure it with a random weighing balance everywhere, it's a big blunder because the acceleration due to gravity varies at the equator and at the poles. So values are not the same thing. So they really be careful about that. I will talk about it tomorrow for sure. Tomorrow we are going to talk about it. But for today, only try to understand about the variation of G with height and depth. That's all. Before I end the class, is there anything you want to ask or say? Anybody has any doubts? No doubts, anybody? I think this is good enough for today. I didn't teach a lot today, I know, but Chetan has a doubt. Okay. Chetan, what is it?
Sir, I confused in the acceleration topics there. You scroll in the second 33 notes, sir.
What 33?
Before
Acha, okay. Yeah.
in
There's
that You said no, sir. On the surface, the acceleration is 9.8.
Yeah.
If the body is flying, if body is prone, then that time we consider it is gravitation due to acceleration is 9.8. No, sir.
Yeah, it is 9.8. Yeah, what's your point?
On the surface also it is 9.8, sir.
Oh, okay. First of all, this is not acceleration, okay?
Okay,
The body is not accelerating, but there is some, okay. Like for on the surface, mg is acting and there is also normal force which is acting. That is why it is not accelerating.
okay,
But
sir.
mg is also still present, right? So that is why I talk about it. That's all.
Okay, sir. Got it.
But if you leave a body in the space, there is no normal force. So the mg creates that A.
Okay, sir. Got it.
Okay, like see how all of those are related. That is what I meant to say. That's what I meant wanted to say. That's all. Okay.
Okay, sir. Got it.
Okay, guys. Then we'll take a break for today. Tomorrow onwards, we'll be talking about more and more ideas. Maybe one or 2 days we will be talking about satellites, which is quite an interesting idea. We will get there and we'll talk about it. All right. Thanks so much and bye bye.